Okay, great, thank you. Well, thank you for coming. Hope I'll give you something interesting. What I want to do is talk briefly about the activities in Computer Security Division and also some of the broader activities at NIST that apply to computer security. And then something that's more in depth, we were asked to talk in detail about one interesting project. So I hope that you'll find this project interesting. And yes, I will try to keep the bureaucracy, et cetera, to a minimum. Okay, so everybody has to have a mission statement. This is our mission statement. But the key point about NIST is that NIST was established to do research in the area of measurement and testing. So it has existed for over 100 years and has been involved in metrology, which is the science of measurement, for all of that time. Probably the best known sort of consumer level thing is the atomic clocks that NIST has been known for many years. The research that's involved in defining standards and measurement accurately is the bulk of what goes on at NIST. We also have, as you well know, anyone who's involved with computer security has probably come across NIST at some point. So we also have a role in computer security. These are just some of the examples of the kind of thing that goes on. We've been involved in computer security for at least 40 years, I would say, going back to the data encryption standard, which was the original publicly available encryption standard that made a big difference in the marketplace. Now, this is an example of the way that crypto standards are done. In this case, it was a request put out from NIST and responded to by IBM. But we followed that up later with the advanced encryption standard, which many of you may be familiar with, was developed through a competition. And cryptographers from around the world submitted their algorithms. They were subjected to analysis by all the other cryptographers, and out of that emerged a publicly available open source strong encryption standard. So that's been quite a success. Some of the other things, we won't go through all of them, but there is also the secure hash family, role-based access control, something that I've been involved in. But I do want to call your attention to the quantum cryptography research at the bottom. That is an interesting field, and if you notice, there are two lines there. One, quantum crypto, the other is quantum resistant crypto. And the first one, quantum crypto research and key distribution, that's a good example of the strengths that NIST brings to this field because, as I mentioned, we have a very, very strong physics lab, 4 Nobel laureates, et cetera, who have done huge amounts of work in quantum physics. And the key problem in quantum crypto is to be able to do single photon production. If all conditions are right and everything works ideally, then quantum crypto really can give you an unbreakable stream. But that is an ideal, and there is an awful lot that's needed in terms of practical implementation. So the NIST Physics Lab works jointly with some of our people at ITL to develop strong quantum crypto using single photon production and also detection. Now the next one, quantum resistant crypto. That's really interesting because you've probably read that if there is a quantum computer developed at some point, then a lot of the cryptography that's out there, basically all of the public key crypto, could be subject to attack because there are well-known algorithms for doing factoring on a quantum computer in much faster time and making it practical to defeat some of the asymmetric cryptography. So that's an effort. The quantum resistant crypto is looking at ways to get around that problem. So take the assumption that there is a quantum computer tomorrow. What do we do to prevent the problems that would occur as a result of that? Okay, here's some of the bureaucratic stuff. 5 different groups. A number of them are involved in research, but as you'll see, there's also one involved in outreach, and there's also some standards and measurement. The last group there, maybe call attention to in this case, this deals with some of the cryptography testing. So if you have a cryptography module, then you can bring it in, have it tested according to a particular standard, FIPS 140, -2, I think it is at this point. So that group, that's just an example of the kind of thing that goes on. Focus areas, just about everything at some point. At the bottom is, again, the validation and testing of security properties. That's a really key point. In addition to the cryptography module testing, there's also work on protocol testing, IPv6 test suite, and so on. Also a lot of research that deals with protocols. The border gateway protocol, this is a big problem, or it's a potential big problem because it needs an awful lot of work in terms of security. Luckily, nobody or very few people have done much to exploit the problems and the weaknesses there, but there's an awful lot of work going on to try to strengthen that at this point. And just about everything else that you can imagine is addressed at some point. Now, delivery mechanisms, that just refers to how we get the work out. Tech transfer is a really big, important issue at NIST. We do a lot of our own research, and that work does get out through a variety of means and gets into commercial products. A couple of the things that are going on now, I've mentioned the border gateway protocol work. There's also an effort right now in attribute-based access control, and this is a joint work with some other government agencies looking at ways to improve access control for systems, which, as you might imagine, is a perennial problem and in need of work right now. Everything else there, we do just about anything, lots of journal and conference publications. Standards, that's something that is important, and I wanted to point out. NIST is not a regulatory agency. We don't specify mandatory standards. We develop standards primarily through working with people like IETF, IEEE, but also some NIST specifications, Federal Information Processing Standards. At this point, that's primarily in crypto, but there are some specifications that are taken up and used widely, such as some of the continuous monitoring and vulnerability management protocols that are out there, secure access protocols. So there's a lot of work that goes on, but we get, again, not a regulatory agency. That's something important to keep in mind. Okay, an awful lot of work goes on reaching out to people. There is a new National Cybersecurity Center of Excellence program which has been started, which is somewhat not independent of NIST, but it is located in a separate facility. They make an effort. There's cybersecurity education program that has been established now, and we have people that go out, try to talk to industry, especially small businesses, state and local governments, what they can do to improve their security. Okay, I'm not even going to go through this. I think you have the slides. Just about anything that you can find there, we'd be happy to talk about. There's an awful lot, but we won't go through that right now. Okay, the key point here. This is the kind of thing that happens all the time. We have lots and lots of congressional mandates. So whenever something happens that raises a concern with Congress, it's very common that they will ask NIST to do something about it. There's a big NIST program in voting that has been going on for some time, security for voting machines. There's an awful lot else that goes on, but the key point here is that Congress typically asks NIST to get involved in a lot of these things, and this is what leads to some of the standards that we had mentioned earlier. The Office of Management and Budget Guidelines, that's significant. Some of the things that come out of our specifications are taken up by OMB, and they basically tell the agencies to operate according to these standards. So that is a case where NIST influences what the agencies do, which then can have an impact on the field in general and on the commercial marketplace. And these are some more examples, some fairly interesting ones there. Smart grid, there's an awful lot of activity in that area. There's a new 300-something page security document that is addressing security for smart grid. And that is very, very new. Cybersecurity in education, I mentioned that as well. And then cloud computing, that's a big, big area. We have some people involved in that as well. Okay, now, I mentioned up front we were going to talk about in depth the project that is helpful in saving money, and in this case it's testing for security or for general software testing. That's important. Just a reminder as to what we are, why we're doing this. We're a government agency, non-regulatory, and our mission is to support industry with better measurement and testing. Now, this project, we've had it going for several years now, and it has been very successful. We'll put up some empirical data to show that in just a minute. We have a tutorial on how to do this particular type of testing that I'm going to talk about. 26,000 and some people have downloaded it, so we know somewhere out there is using it. But we also have several hundred organizations that are using it. These are, at the bottom, are not the organizations that are just using it. These are people we have done joint work and joint publications with. So tremendous amount of interest, especially in the aerospace field, as you can see on the right. So, as I mentioned, better testing is needed. We know how to do ultra-strong testing for at least functionality with not necessarily security, but we know how to do ultra-reliable software. The problem is it's much too expensive. So one of the things that we need to do is reduce the cost of testing for software functionality in general, but it's also important that there's an awful lot of exploitable vulnerabilities, probably half, that result from just mistakes in code. This is at the bottom a graph of vulnerabilities and the number of vulnerabilities reported in the National Vulnerability Database, which NIST maintains. This covers vulnerabilities publicly reported, nearly all of them. There are a few very small products that don't make it in there just because they're not used very widely, but just about all vulnerabilities that are publicly reported are in this database. So at the bottom we have a list of the kinds of problems that are reported: buffer errors, memory management problems, memory leaks, and so on. You put all that together, and the vulnerabilities that can be not just vulnerabilities, but can be problems for software in general, account for about half. So that's why we can get some security bang for the buck by doing general software testing. If we remove these basic errors up front, that reduces the vulnerabilities that find their way out into the field. And we also have some specialized approaches to testing for security problems, including buffer overflows and network problems. So I wanted to put this up right up front. So this is why the rest of this talk is worth listening to. Lockheed Martin did a 2.5-year study looking at 8 different pilot projects and concluded basically that this approach saves roughly 20%. It varied, of course, by pilot project, but roughly 20% of test development costs. And so that's very significant. As you know, testing covers probably about half of the cost of most software development efforts. In some cases, much more than half of the cost of the development effort. So they also improved test coverage measured in different ways by 20 to 50%. So that's pretty significant. Here's an even more interesting one. This is Rockwell Collins, and they looked at how to do MC/DC testing. So modified condition decision coverage is the testing used, required by FAA for level A software, which means basically software that can lead to an aircraft crash. So serious life-critical software. It's extremely expensive. The cost involved is enormous. So what they were able to do was show that you can use this approach to reduce the cost drastically. So some numbers here: 47,000 test cases. This was for about a 600-line piece of code, module within that 196,000 software-defined radio package. So an awful lot of tests, but it was able to be done very quickly and inexpensively. That's the key point. So as to how we got to this point, well, about 10, a little over 10 years ago, we had a project that was looking at what causes failures in systems. So what we wanted to look at was, number of possible causes, logic errors, there can be calculation errors, and so on. We reviewed 15 years of FDA medical device data, medical device recall data, and looked at what causes the problems. And one of the things that stuck out was what we call interaction faults. Now, what we have right here in the center says interaction fault. For example, we have a failure that occurs if the pressure is less than 10 for some device, say an infusion pump, and the volume is greater than 100. So two separate factors are involved in that failure. And at the bottom is an example. So we had a failure when the altitude was set on 0 meters and the total flow was less than 2.2 liters per minute. So there's an example of two separate factors that are involved. Now, here's some examples from the National Vulnerability Database. So in blue at the top, we have a single, what we'll call a one-way interaction, but a single factor involved in a failure. In this case, your typical problem, somebody didn't allocate enough memory to read the data into. But the second line is a two-way interaction. That's more complicated. So we had a failure that occurred when there was a single character search string and a single character replacement string. If you had a test that had one of those conditions true, but not both, then that test would pass. You would not detect that problem. So this was an error that was out there and sort of lurking because maybe the testing never exercised that particular case. And then at the bottom, we've got an even more complex problem. We've got three factors involved. So this particular problem would not manifest itself. And again, these are buffer overflow errors. So these are complex interactions that can basically bring down your system. So serious stuff. Three-way interaction at the bottom. So these three factors had to be true in order for that vulnerability to occur. So here's an example of what this might look like in code. Two factors. The one I mentioned before, altitude adjustment is 0, volume is less than 2.2. So if the altitude is 0, we do something, and then we come along, and we have the next condition evaluated true and fall into some faulty code. So if we have a test that includes, for example, altitude of 0 and a volume of 1, or any number that's less than 2.2, then we would trigger this problem here. However, if we had a test that had only one of those conditions true, then we would not necessarily detect that problem. So this is how the interaction faults are distributed in the FDA data that we looked at. So in this case, the y-axis is the percentage of faults detected. So roughly 2/3 were triggered by a single factor, and better than 95% by two factors, and we didn't see anything that involved more than 4 factors. So this is kind of interesting because these are medical devices. Most of these, maybe not all of them, but most of them could be life critical. So that's the distribution of errors for that application domain. Somewhat old data. This was data that goes back to the 80s in some cases. But we looked at some more domains. So this is the fault distribution for a server open source module. Now these faults are a lot harder to trigger than the ones in the medical devices, which is sort of disturbing because the server is presumably not life critical. But in this case, a little over 40% were triggered by a single factor and about 70% by 2 factors. And going up, we had some cases where there were 6 factors involved. So that's a very complex error where you've got to have 6 things true in order to trigger a failure. But as you can see, the curve goes very rapidly, so this is cumulative faults tailing off at an interaction level of 6. Looked at a browser, same sort of pattern that we see there. In this case, fewer faults were manifested at one-way interaction, less than 30%, but a little higher level at the level of two-way interactions. But again, the shape of the curve is quite similar. Here's database software. In this case, this was development software, so the light blue line is different than the browser and server because those, and also different than the FDA data, Those others represented fielded products. The light blue line represents development testing. So these tests may be the result of very first time testing the software. So that's why those faults are probably were easier to detect than the others. Here's another one. In this case, we looked at seeded errors. So before we looked at errors that are reported in the field, but we wanted to consider the case of where errors are seeded. So this is a very common package developed by Siemens Research, and it's used an awful lot in testing evaluations. So the idea is you've got a set of software, contains known errors, you use your testing method on it, and try to determine if you're able to detect all of those faults. And in this case, we didn't see anything that required a test of more than 5-way interactions. So that's consistent with what we saw in the real-world products. In this case, though, if you look at the location of the line, this suggests that the researchers worked a little too hard in making their seeded faults. So these seeded faults were actually harder to detect because the line is further to the right than the ones that were in the real-world products. And last but not least, network security software. Someone else, not our group, did this. But the curve is similar again, and we have 5-way interactions at the top. So we didn't see any interactions that involved more than 5 factors for this particular set of software. But the curve is very similar, although less than 20% were triggered by a single failure. Now, the likely explanation is that an awful lot of this results in how many users there are. So the browser and the server, the network software, have literally millions of users, whereas the others didn't. So summing it all up, the number of factors involved in the failures is very small, and that means we can test 5-way interactions or 6-way interactions with very few tests. And the way we do that is with some new algorithms. But this is basically just summing up this knowledge and what we do about it. So the interaction rule, we say that most failures are triggered by 1 or 2 factors interacting, and progressively fewer by 3 or more factors. And we haven't seen anything yet, and no one has reported to us a failure in the field that involved more than 6 factors interacting. So what do we do about that? How does that help? Well, this is how it helps. If we know that, let's say we've got experience with a particular type of product, and we've never seen a failure in this type of product that involved more than 4 factors. So that means if we do all 4-way combinations, then we don't have to do fully exhaustive testing of all possible combinations. We do all 4-way combinations, or maybe more all 5-way combinations, and we have a very strong probability of detecting the faults. Now, there's not a guarantee because there are timing issues, there are lots of other issues that are involved, and you also have to do the same kind of thing you have to do with any testing, which is some form of category partitioning, where you've got input variables that have a large, or essentially, say 2 to the 64th range. We've got to select points in that space that matter. So you have to do that, but if you do that model right, then you can get very strong testing. So again, if we can do all 4, 5, 6-way combinations, then we have very good testing. And the empirical data backs that up. So how this works in practice, here's an example everybody's familiar with. Think of these as 10 binary variables, on or off. So how many tests would we need? Well, if we did all possible combinations, we need 2 to the 10th, obviously, 1,000 tests. That's probably too much for a word processing program. But we could look at all 3-way interactions. So how many tests do we need to cover all 3-way interactions? Well, we know that there are 10 variables. We've got at least 3 interactions per test. So that's something we could start with, but there's more. The number of combinations we need is actually 960. But we can pack a lot of variables, or a lot of combinations into a single line. So does anybody want to guess how many tests we would need to cover all 3-way combinations of these 10 binary variables? Any guesses? I tend to put this to graduate school classes and undergraduates, and usually somebody will come up with an answer, and the answer is usually something on the order of a few hundred. Well, the answer is 13. So we can test all 3-way combinations with 13 tests. So that's very powerful. In this case, each row represents a test. Each column represents one of those 10 binary variables. Now, this is what's known as a covering array, and it's a particular type of matrix. The theory behind it was developed in the 1990s, but it's fairly simple to understand. The key property is that any three columns picked in any order, in this case three-way, contains all possible three-way combinations of those values. So again, we've got binary values, 8 possibilities, of course. So if you look in any three columns picked in any order, left to right, right to left, inside out, we'll have 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. They're all there, like there or there. So it's a very hard problem mathematically, but there are good algorithms, and the project has developed some of these. Here's a bigger example. In this case, we've got 34 switches. So let's say we have this panel, and we've got some software behind this panel that's supposed to interpret the way those switches are set and do things differently depending on what combination of switches is set. So that's 2 to the 34th, or about 17 billion combinations. And we can't possibly afford 17 billion tests. So again, we're going to use what we know based on the interaction rule, that the number of factors involved in failures is small. So we could look at testing 3-way, 4-way, 5-way, 6-way combinations. For this set, we only need 33 tests to test all 3-way combinations, 85 for 4-way. I didn't put the 5- and 6-way combinations up there, but they're on the order of a few hundred, 500, 600 or so. So the key point is, again, we can use a very small number of tests to get very strong testing. So what we might do, let's say we wanted to test 4-way combinations, so we can use 85 tests. Going back to our graph of the way failures occur and the way they're distributed, we see something on the order of that 90% plus fault detection. We can't guarantee that. That's based on empirical data. There is no theory that can show. It's easy to come up with a counterexample that would disprove this, but for the real world, empirical data says that we're going to get better than 90% fault detection. So again, it's not theory, but it is empirical data based on thousands of failure reports. Here's an example looking at simulation. That we think that's a really interesting area. We have a network simulator. The idea here is you have a network and you can configure it. It's a grid computer network, configured in different ways. In some cases, you can lead to deadlock because of the way you've configured your network. The number of nodes, the number of buffers, buffer size, and so on. So we looked at different ways of approaching that. One is simulation, where you look at your typical Monte Carlo simulation, but then we looked at improving that using the combinatorial approach with covering arrays. And what we found was that we would get much better detection of deadlocks. So in this case, 14 deadlocks out of an enormous number of possible combinations. But the combinatorial covering array approach is at the top. The bottom is basically your typical random testing, random simulation that's done. And so the random simulation, you were able to find a lot of problems, but nowhere near as many with the same number of tests. So again, we can use fewer tests to detect problems that could occur in this network. Now, if you're concerned about setting your network up accidentally, such that it leads to a deadlock, you probably don't have too much to worry about. As you can see, something on the order of 4 times 10 to the minus 7th probability of finding one, or of having one of those configurations occur by itself. But if you're concerned about forcing somebody's network into a deadlock, or someone else forcing your network into a deadlock, you've got much more to worry about, because in that case, somebody's out there looking for it. So you need to find those deadlock configurations before somebody else does. Here's an example that we did for the Air Force. They have an interesting problem where they've got, say, a laptop like this one. This is not theirs. This is off the net, but this is the basic problem structure. They have a laptop. It has a lot of fairly exotic peripherals, targeting equipment, UAVs, all sorts of things. And what they found is that in some cases in testing the software in the past, plugging the peripherals in the wrong order or the way that the developers didn't expect leads to a problem. So they said, can we use the same approach to reduce the number of tests needed to detect problems in plugging these peripherals in? So it's basically an order of events problem. And so yes, we did do that. In this case, let's say we had 6 events or 6 peripherals to plug in. That's 720 possible tests. But with only 10 tests, we can cover all 3-way sequences such that there's some interleaving among those events. So if the key problem is whether event A occurs before B occurs before C, we can detect that with a very small number of tests. For example, in the matrix, if we look at anything and then C and then followed by 0 or more events and then F and then 0 or more events and then B, we can find that at row 6. And any 3-way combination we can find in this matrix. Some tools that are available. The main tool is the covering array generator, and we'll go into some more detail on that in a minute. That's the tool that generates the matrix that I put up earlier, for example, with that word processing example. So that'll generate up to 6-way combinations very efficiently, and I'll show you some numbers on that. The sequence covering, we talked about that. Coverage measurement, this is really important because if you want to use this approach, it's good, it's effective, but your organization probably doesn't want to turn over and disrupt all of the development and testing practices just to bring in this new approach because it may not be fitting for your organization or what. But there are established approaches that you don't want to disrupt. So what we can do with this measurement tool is we can take those tests, measure the coverage that they provide, and then add additional tests to give you, say, 4-way coverage of combinations, or 5-way coverage, or 6-way, whatever is needed. And then some more specific tools, access control policy tester that applies this approach, and so on. Now, I mentioned that the algorithms are much better now, and this is a hard problem. This is an example. So here, there's a problem that has 10 variables. We want to test the problem with 10 variables in this configuration at the bottom, 7 binary, 2 3-value variables, and so on. For 5-way combinations, the red oval circles the number of tests that was produced by our algorithm, 4,200 tests, where in this case, fewer tests is better. You want fewer tests that cover the same level. So 4,200 and some tests produced in 18 seconds. Another tool that was out there ran for more than a day and didn't produce anything because it just ran out of time. Some of the others, again, they're all quite a bit larger test sets than what ours did. So this is a significant improvement over the state of the art before. Now, there are lots of good algorithms out there now. This was one of the first ones. Microsoft has a product called PICT, which is it's free. It's a research tool available. You can download it. It generates covering arrays as well, and works very nicely. So, I'm not selling any products. I'm trying to convince you of the value of this particular testing method, but you can use it using other tools. Here's an example of how this particular tool works. We would define a set of variables and their possible values, and that's what's shown on the right-hand side of the panel. On the left-hand side is where we would define them. It steps you through. It makes it easy to define. But we have at the top a variable called current vertical separator, 3 possible values, and 11 more. So you can see how this works. It's fairly easy to set up your variable and possible values. This is really important. This is one characteristic that makes our tool significantly better than most of what else is out there, is the ability to support constraints. A constraint, an example, your typical example is, let's say we have an app that we want to be able to run on Linux or Windows environment, or maybe some others as well, but when we want to test that app, we want to set up configurations for the different environments. We're never going to see Internet Explorer running on a Linux system. So we've got to generate tests that cover 3, 4, 5-way combinations that do not include any test that specifies Internet Explorer running on a Linux system. Because if we did, the test would not only be wasted, we'd also we would lose the combinations for other variables within that test. So we've got to be able to eliminate those. So we have very good support for constraints to prevent that from happening. We can also do variable strength interactions. So let's say we've got 3-way coverage that we want to do for a large set of variables, but there's a subset that we want to do for 5-way combinations. And we can do that. We can say cover everything to at least the 2 or 3 or 4-way level, but select out a small subset that should be covered to a stronger level. And so we're able to do that as well. This is what the output looks like. Each row is a test. Each column is a variable. And then those are the values. We have an awful lot of users, very strong in, well, IT, of course, no surprise, but defense and aerospace, and also finance. So that was kind of interesting. And I actually know more about what the defense people are doing. I know what the Air Force is doing with it and what weapons they're testing. I don't know anything about what the finance guys are doing, but they really like this. So that's kind of interesting. Telecom also. Telecom is another case where you've got very complex software and a lot of money riding on it. Some more options for the output. We can put everything out as a matrix. That's good for post-processing with shell scripts and so on. We can do human-readable configurations. That's the kind of thing where you might do what I mentioned before with setting up a test configuration where we've got Linux, Windows, Apple, Android, and so on. So we can set up these configurations to make them more human-readable. And contact information. We have a website with lots of conference and journal papers, PowerPoint presentations, basically just about anything. And feel free to contact us. We love to talk about this. As I said, we've got a lot of people that are using it, and the empirical data suggests that it's useful. So we're always interested in working with people. We learn a lot more by working with people than we do just trying to come up with it on our own. For example, the Air Force problem that we talked about earlier, the coverage measurement problem as well. That was done. We did a coverage measurement of some NASA spacecraft software, looking at, was the coverage good? Because this was, after all, space software, very strong testing, several thousand tests. So they said, well, maybe it covers all 2 or 3-way combinations. And so we measured that, and we actually developed a measurement tool in that case to do that measurement and then turned it into a part of the package. So again, just an example of the kind of thing that we find useful in working with people, and we'd love to work with anyone. So any questions? Yes? In some cases, yes. In some cases, no, just black box. Okay, for a large set of variables, yeah, the question is, can we generate tests for a large set of variables? The answer is yes. The interesting thing here is that the number of tests that's produced is proportional to 2 factors. It's proportional to the number of values raised to the power t, the t-way interaction, so 2, 3, 4-way combinations, and the logarithm of the number of variables. So that's a nice property, because if we have 50 variables and we want to be able to test 100 variables, it doesn't add that many more tests. The critical point of though is the number of values per variable. So you need to minimize that. But you need to do that for any sort of testing where you need to do some sort of category partitioning. So yes, we can handle large numbers of variables. We've had one user that's done a 358 variable problem, and it works fine. That's aerospace, spacecraft software again. Any others? Okay. Oh, great. Thank you.